Yeah, so I'm talking about Signal's double ratchet algorithm. Specifically, we're going to talk about the history of Signal and the double ratchet, Signal the protocol, Signal the app, and then get into some of the more specifics about the double ratchet itself, which includes the KDF ratchet, the Diffie-Hellman key exchange, the Diffie-Hellman ratchet, and then how that all comes together, some pros and cons of this encryption method, and some lessons that we in the cryptocurrency, blockchain, DLT, whatever you want to call it, space can learn from it. So for the history, well, it's contained in this Open Whisper Systems, which is a container organization, I guess, that maintains Signal and the double ratchet. And then they also have some other projects. They're like a foundation, it's their job to maintain it. It's open source, so there's other contributors, but it's kind of their thing. It's created by a guy named Moxie Marlinspike, which is an awesome name. So the double ratchet algorithm itself was developed in 2013, and then it was introduced into the Signal protocol in February of 2014. Important to note that the first Snowden leak was on June 5th, 2013, so as this was kind of getting finalized at that point, we'll talk about that a bit more later. Also developed by Moxie Marlinspike and Trevor Perrin, and it was initially named Axolotl Ratchet. Do you know what an axolotl is? It's like a salamander that can regrow its arms and organs and its brain if it needs to. But it was confusing, and so they changed it to Signal to say the app, and the double ratchet for the thing. So a little tangent for a second. There's this documentary called Hold Fast that is about this boat, and these 4 people found that since fiberglass is pretty much indestructible and it doesn't really degrade, you can get sailboats for really cheap that are abandoned, and so they bought this boat and fixed it up and was sailing around. In middle school, I watched this a lot, right as I was kind of finding out about this punk anarchist DIY hacker thing, and I watched it a lot, and I loved it, and I highly recommend it, actually. It was made by Moxie Marlinspike, the same guy that made this, so it's this documentary blew my mind, and then Signal blew my mind, and it's the same guy, so it's this exponential mind-blowing from the same person. That doesn't really have anything to do with anything else. It's just cool. So I'm going to talk about the Signal protocol for a second. It's kind of a wrapper for the double ratchet algorithm. It deals with a lot of implementation details with real-world stuff, like getting messages out of order or really long latency or whatever. It's not federated, so there's not a consensus algorithm going on, but it is end-to-end encrypted for voice, video, calls, and instant messages. You could use it for just anything if you wanted, but that's what it was designed for. It uses a double ratchet to encrypt all the traffic. Some of the other cryptographic primitives that it uses are the curve 25519, AES 256, and HMAC SHA 256, which are pretty standard. It was also previously called text secure. They keep renaming stuff. So it's used in the Signal the app, which is open source and is made and maintained by the Open Whisper systems. It's also claimed to be used in WhatsApp, Facebook Messenger's secret conversations, and Google Allo's incognito mode. I say claimed to be used because these are all closed source, so we can't really verify it.
Is there anybody saying that it isn't? Like they've looked at the... No.
Not that I know of. But they kind of, in my opinion, did it badly. So here's some screenshots demonstrating Facebook's secret conversations. So over here, it's just the regular unencrypted conversations that's data mined and sold. And then to start a secret conversation, you have to like go into their contact. And I don't know if you can read it. This option says secret conversation, and then you start it. And then it defaults to the unencrypted way. Also, in the specific example, this person who they're messaging is like doing some bank work on behalf of whoever owns this phone. So they're like, oh, what's your bank account number? And they're like, oh, I don't want to send that unencrypted, so I'm going to do secret conversation and then send it. But as an attacker, if I see all of this unencrypted, and they say, what's your bank account number? And then 3 unencrypted messages. I know what's in those messages, and I can for sure be confident that if I spend the resources to break them, that's a good target. Yeah, we're kind of in this crypto wars too, where they realize that they can't prevent people from having strong cryptography, but now it's like the defaults are weak cryptography. So that's kind of a ongoing thing. But the Signal app itself is open source, an open source implementation. It's free, both free as in speech and as in beer. And there's clients for Android, iPhone, Windows, Mac, and Linux. And it's really awesome. It's like the user interface is really great because you don't know any of this cryptography stuff is going on. Like, you don't have to deal with it at all. It's just a regular texting app that is the same or better than the one that came with your phone. And yeah, it's great. So to go over some of the accolades that they've got, let's see if I can see it. Snowden says, use anything by Open Whisper Systems. Laura Poitras says, Signal is the most scalable encryption tool we have. It is free and peer-reviewed. I encourage people to use it every day. Bruce Schneier says, I am regularly impressed with the thought and care that put into both the security and usability of this app. It is my first choice for an encrypted conversation. And then Matt Green says, after reading the code, I literally discovered a line of drool running down my face. It's really nice, which is quite the recommendations. Yeah. So yeah, these are pretty great reviews. And then from the other side, this is a leaked NSA PowerPoint slide that was made in 2012. At the time, they were using this ZRTP VoIP client. It's a different encryption algorithm because this was in 2012 before the double ratchet. But even then, they said that Signal was catastrophic to their surveillance capabilities. Okay, so let's get into the double ratchet itself. The whole idea is that you can regenerate the keys anytime you want using symmetric AES-256 encryption. And you generate these new keys in a deterministic way. So you're pretty much changing the keys that you're using anytime you want. It provides future secrecy. These terms are a bit weird. future secrecy means if a future key is compromised, the current key is still safe. And then it also has backward secrecy, which means if a past key is compromised, current and future keys are still safe. This is the self-healing property, which is why it was originally called axolotl, because of the self-healing salamanders. So what is Ratchet? It's used for deterministic key generation. It's built around this KDF, or key derivation function, and you pretty much take the output of that as the input to the next call to that key derivation function. It's also a one-way function, so it's like a hash. You can go one way, but you can't go backwards. It's a lot like BIP 32 and 44 from Bitcoin, conceptually. Signal uses 3 ratchets: a send ratchet, receive ratchet, and then a Diffie-Hellman ratchet. There's 3 ratchets, but it's called the double ratchet because the send and receive are both conceptually the same thing. It just makes implementation a lot easier, which we'll get into now. So symmetric key ratchet generates the actual AES keys that you use for encrypting your message. It's generated with the KDF chain, which takes a secret and a key and generates 2 output keys. Like you can see here, you have an input KDF key and then the next KDF key and then the output key. You would encrypt the message with these output keys. And in Signal, there's 1 chain for sending and 1 for receiving, which makes implementation easier. It's kind of like BIP 32 and 44 again, but this is like a list rather than a tree, which is the BIP 32 and 44. Silent Circle Instant Messaging Protocol, which is a kind of older instant messaging encryption, used this, but it was like just this part, which is still cool. The main properties it gives us is resilience, so that the output keys appear random if an adversary doesn't have the KDF key, even if they can control the input. So these you can't figure out if you don't have these KDF keys, even if you can control what is put in. Again, it has forward secrecy, so the past keys appear random. So if you have this key, you can't go back and find out what this key is. And then the break-in recovery or future secrecy, backward secrecy, means that the output keys appear random if they have 1 KDF key. So if, say, this one was compromised, these future ones are also safe if these inputs have enough randomness. That's not present in BIP 32 and 44. If you get one of the keys, the whole bottom part of the tree is completely compromised. And this is kind of the main heart of the whole algorithm. So do people know about the Diffie-Hellman? Okay, wait. So kind of take what I was just saying and just kind of store it. Have to do a context change and explain some other stuff, and then I'll get back to that. Okay. So the Diffie-Hellman key exchange, it's a cryptographic primitive that is used all over the place. It allows 2 parties to agree on a shared secret without any listener being able to find out that secret, and it uses modulus arithmetic. So to break this you have to break the discrete log problem, which is very hard and, as far as I know, not possible at all. This is used in the Diffie-Hellman ratchet, which is a separate ratchet. So each message that gets received has a header with the Diffie-Hellman public key that was used, and then if the key that is in the message we get is new, if we haven't seen it before, we do a step on our Diffie-Hellman ratchet to later generate the key that was used to encrypt that message. And the output of this Diffie-Hellman ratchet is used as the input to the symmetric keys. So it's used to like modify them. So I have some diagrams from the signal document. So this message from Bob comes over to Alice with the public key, and she does a Diffie-Hellman on it and gets the output, and then she can send a reply back to Bob, and they can get the same output. And it's just this kind of like back and forth where they're each extending their ratchet, and each time they get the same outputs, which only they can know because of the discrete log problem. And yeah, these outputs are used as the inputs to the symmetric key, which we'll see in a bit. And this provides the break-in recovery feature because the future keys appear random because we're always modifying that input based on the output of this Diffie-Hellman chain. And a kind of implementation details that they advance twice for each message, once for the receiving chain, once for the sending chain. Okay, so let's go over a kind of, okay.
Just to clarify, the chains, are they key chains, like a set of derived, a chain of derived keys?
Yeah. Yeah, they're derived with one key and then an arbitrary input, and the output of the Diffie-Hellman chain is the input to the sending and receiving chains to provide the entropy, or appears to be entropy, to a person who doesn't have the keys. Okay, so let's go over a diagram of what actual communication looks like. But I just want to point out, this diagram is made by me, and this diagram is made by Signal, so like, don't ask me to draw pictures for you, I guess. So here we have Alice and Bob, of course. They both have their Diffie-Hellman chains and a send and receive chain, and you see that Alice's send chain is the same as Bob's receive chain, and Bob's send chain is the same as Alice's receive chain. So if Bob wants to send a message, he clicks over his send chain and gets a key, and then encrypts the message with that key and sends it over the internet to Alice, who then she can see the public key, so she ticks over the receive chain, generates the new key off of the receive chain, and since the chains are kind of swapped, where Alice's send is Bob's receive and vice versa, these keys are the same, and it's symmetric AES encryption, so she can just decrypt it. And then they update everything. In the double ratchet program or standard itself, you can update this whenever you want, but in the Signal protocol and the Signal app, these are all updated every single message that you send. So they each tick over the Diffie-Hellman chain twice and get 2 keys, and that use those as the inputs for the next call of their. And then it's just the reverse. If Alice wants to send to Bob, She takes over her send chain, gets the key, encrypts the message, sends it, and Bob takes over his receive Ratchet to get the same key to decrypt the message. And so the output of these Diffie-Hellman chains are modifying these send and receive chains, which is how we get the self-healing, was because it's new entropy every time from an attacker's point of view. So some pros and cons of it. Some pros is that it's awesome. Yeah, it's very secure, like very, very secure. There's been tons of analysis and people trying to break it, and there are no known attacks from a cryptographic standpoint. It's self-healing, which is like the main thing to me, that it will, if you're talking with your friends for hours on end, someone builds a supercomputer and breaks one of the keys, they get a cat meme that you sent. Just one, not the whole conversation, just that one message, and they've wasted all that time, all that supercomputer. Or if they got it some other means.
Or the nuclear codes, depending what happened to be sent.
Yeah. Yeah, exactly.
Makes it scams.
Yeah. So the Signal app, I talked a little bit about it. It's very user-friendly. Like in blockchain a lot, we're trying to make it so that not technical people can interact with it, but the Signal app itself is the easiest to use cryptography I've ever come across, and it's also among the strongest cryptography in the world. And it's really fast, actually. Like, you think all of these chains will add a lot of latency, but it doesn't really, because you can make audio and video calls through the Signal app, all encrypted with this double ratchet.
Single Diffie-Hellman per voice call?
No, it's like each packet gets a different.
Seriously?
Is my understanding. Okay, yeah. Yeah, we kind of have this perception that doing all this cryptography stuff will make things slower, but that compared to encoding an image is like other things that we don't really think about take a lot more computing power and time and network and stuff than the cryptography, which we think a lot about, and so we think it's kind of a false perception thing. But yeah, they started using the double ratchet encryption in March of 2017 for voice and video calls. Some cons are there's side channel attacks, which I can't really fault Signal for because everything has side channel attacks. When the Vault 7 CIA leaks happened, there was some talk about how, oh, they broke Signal, and everyone was freaking out about it. But they didn't, because their attack was to take screenshots of the decrypted messages or put a keylogger in to see what you're typing. And Signal's not protecting against that. And yeah. The other big con is that there isn't really any metadata resistance, which is, I pointed out earlier that the development of this happened, was ongoing and finished soon after the first Snowden leaks. So at that time, we didn't really realize how important metadata is. Yeah, but Signal is always updating stuff and changing, and Signal started before the double ratchet was started, and they're always updating to use the best and most secure encryption. So maybe they will have a project to add some metadata resistance. So some things that blockchain can learn is we always are like have this like sacred attitude towards keys. It's like, this is the key, it's forever, you don't ever change it. But you can get some really good good stuff like this self-healing if you're like, oh, it's a key, it's one use thing, use it once, never again. And also be able to change. Like, immutability is great, but if it's not adding a lot to your project, it might be preventing you from doing cool stuff like this. And then also make it easy to use for non-technical people, not sort of technical people who have heard about it and know what an address is, but people who've like never used it, never heard of it, can just like install the app and use it. Because I think some people have like installed the Signal app because the interface is better than their stock texting app rather than all this encryption stuff, which is like awesome because they don't have to spend however much time to understand it. So yeah, that's, if you saw my diagrams, this interfaces stuff is really not my expertise, but it's important. So maybe Brian or a designer can look at Signal and see what makes it so easy to use. Okay, question.